Huh? So your quiz on 2.1 and 2.2 will be on Wednesday. Okay. Because I want to make sure that you are actually really, really ready for it. Okay? Because we have not yet covered the things that are not stresses, which is on page 57. Okay. So the effect of a catalyst, 57. So when is your quiz? Wednesday. Okay. And if that doesn't work for you, just let me know. We can make an alternate arrangement, okay? So let us remind ourselves, how does a catalyst work? Tell your partner, how does a catalyst work? Okay, the catalyst provides an alternate pathway with a lower activation energy. And guess what? That lower activation energy is applicable for both the forward and reverse. And it actually speeds up both rates by the same amount. So both rates are still going to be equal. They will both be faster. So both rates will be faster, but they will still be equal. And so there will be, if they are both equal, then there is no shift. So let's have a system that starts at equilibrium. Let's draw the rate diagram and the concentration diagram. We are on page 57. Okay, so now we add a catalyst. The forward rate increases, the reverse rate increases by the same amount. And because those two rates are still equal, there's going to be no shift. And if there's no shift, there will be no curve. So what do these do at this point? They just stay flat, flat, flat. All right, now we have concentration versus time. And we've got a really easy system here. We've got A and B. So we've got A and we have B. And here we add catalyst. I would like you to tell your partner, what do those lines do at that point? Discuss. What do those lines do when we add a catalyst? So, ladies and gentlemen, where should the spike be? Where should the spike be? Or is it a trick question? It's a trick question. Where's the spike? There's no spike. We've got A and B. They're still being swapped back and forth at the same rate, right? It's just that before it was like, woo, woo. Now it's like, woo, woo. But we're not changing the concentrations, so there is no spike. No shift. Okay, so right at this time here, nothing happens. Woo! You don't have to draw those little dots. I'm just kind of doing them like dots are unnecessary. Okay, now we are going to talk about, although a catalyst has no effect on the position of an equilibrium, which means we don't have more reactants, we don't have more products, it doesn't shift. It does mean that if we are not at equilibrium, that we will reach equilibrium faster, okay? So let's say that we have a container. Let's say we have a container and it either contains reactants only or it contains products only. So we are going to have our rate diagram where we have we're starting with reactants only. So let's see what we get. Now, without a catalyst, what would this look like? We're starting with reactants only. You should be able to tell your partner this. We have seen this graph numerous times now. Tell your partner, what is the forward rate like at the start? What is the reverse rate like at the start? If we have reactants only, we have lots of A. How much B do we have? 0. So what is the forward reaction initially? Fast. Yes, because we have lots of it. What's the rate of the reverse reaction initially? 0. Tell your partner, what shape do those curves make now? Do we like what I've drawn? No. Okay. Better? No. What's wrong with that? That's an S curve. Okay. Better? No, it should be a curve. What do you think? No? They're not what? They're as equal as I can draw them. Okay, so if you draw them like this and you're like, I'm trying to tell you, Ms. Spence, that those are equal, I will believe you, because that's as good as I can draw them. I'm not really that good at drawing, okay? I will assume that you're like, yes, those are equal at that point. Because you know what? If we back away far enough, it kind of looks like they're equal, doesn't it? Yeah, okay, right? From a distance, they look equal. Okay. Now, this here, actually, I should say that this is forward and this is reverse. And then we're going to have forward catalyzed and reverse catalyzed. What would happen to those curves if we then decided to catalyze it? What would happen to our initial reverse rate? It's still 0. What would happen to our initial forward rate? It would increase. So we should have now forward catalyzed. Reverse catalyzed. Now, what should those two lines do? What shape should they be compared to our original without the catalyst? It should reach equilibrium faster. So here we have uncatalyzed equilibrium, yes? So and that's at this time here. So we should reach equilibrium faster. And once we reach equilibrium, what is true of the two rates? They are the same. And should they be at the same level as the uncatalyzed ones? Should they be higher? Should they be lower? Well, they're going to be the same as each other, but they should be higher. Okay, so what it should look like is it should look like this. Whoops, come back here. Right, because here we have reached catalyzed equilibrium. Are you ever going to have to draw this graph? No. To be honest with you, no. But it gives you an idea of what's going on, okay? All right, let's try our concentration diagram. Here's our concentration. Here's our time. We got A. We got B. Where does the concentration of A start? High. Where does the concentration of B start? B starts at not just low, but 0. What will happen to the concentration of A as time goes on? It will decrease. What shape will it take in that decrease? A curve. Yes. Fast, steep, shallow, flat. Yes? And B should also go steep, shallow, flat. Now, I've just randomly chosen how much they change by. They could cross over, you know what I mean? Like, I don't have any, as long as the changes are the same as each other, it doesn't really matter. Now, what if we now have A catalyzed and B in the catalyzed reaction? Where would A start? Different place or same place? Same place. Where would B start? Same place, different place? Same place. Will there be anything different about these curves? Will the final concentrations be the same or different? The same. What should happen to the curve part? Should anything happen to the curve part? It should be faster. So how are we going to make that faster? We're going to make the curve steeper so it gets down there faster. Yes? And B should be faster. Are you going to have to draw that graph? No. Is good though? Ella, I have this for you. It's been a long time ago, but every time I remember to have it back, it's the day when you're away, and then every time you're there, I think I have it back. Okay, now, this is actually wrong, so just cross this out, because it is just wrong. It's a beautiful diagram, and I'm really happy that someone made it, but they didn't do it correctly. So just cross it out. I have to now go and fix it, but you know, whatever. You don't need that diagram anyway, so it doesn't matter. Yes? Pardon me? You don't, no, because the catalyst is already there at the start of the reaction. It's just either with catalyst or without catalyst. Yeah. All right. Concentration diagram, starting with reactants only. Diagram A, diagram B. Either of these are correct. Yes, you can have a crossover or you can have no crossover. In this case, in diagram A, which side is favored? When I say favored, I mean has a higher concentration. Which side is favored? Whoops. Has a higher concentration at equilibrium. So in diagram A, which side is favored at equilibrium? Is it reactants? Or is it products? Products, yes. Okay, so for diagram A, the products are favored. Now, I don't remember, I sort of did KEQ with one of the classes and not with the other class. Did I do it with you guys? KEQ? No. No, okay, we're gonna talk about KEQ. KEQ is the equilibrium constant. Do you see how I spelled it there? That's why it's a K, because it's a constant. And what it is it is the ratio of the concentration of products over the concentration of reactants. Where can I write that? Maybe up here. This ratio is constant as long as you don't change the temperature. That's why it's called the equilibrium constant. As long as you keep the temperature the same. This is a wee little preview of what you're going to be seeing in 2.3, okay? So it doesn't matter what you do to a system. You can throw extra concentration in there. You can squish it and change the pressure. You can do all those things. The ratio of products to reactants will stay the same unless you change the temperature, in which case the K value will actually change. Okay? You can throw a catalyst in there. The K value stays the same. That ratio of products to reactants stays the same. So let's just bop down here again. Okay? So we have our KEQ, which is the equilibrium constant. And remember, KEQ is equal to the concentration of products over the concentration of reactants. So P over R. And in this case here, what can you say about the amount of product compared to the amount of reactant? There's more. So here we have a large product over a reactant. So if you have a big number over a small number, what do you get? You get a value which is greater than 1. Okay? So when we say that the products are favored, that also means that the KEQ value will be greater than 1. Now, in situation B, who is favored at equilibrium? The reactants are favored. So if we write our KEQ here, that's our products over reactants. Now the products is smaller, it's a small value, and the reactants is a big value. And a small number over a big number gives you a value which is smaller than 1. Okay, so when reactants are favored, that means that KEQ is going to be less than 1. This is not on the quiz Wednesday. Okay? However, it's always nice to have seen something a couple of times. So that's why we're just introducing it briefly here, and you'll see it a whole lot in section 2.3. All right, in diagram A, the position of the equilibrium sits more towards the right, towards the products. And so we say that the system favors the products. And if the system favors the products, is KEQ bigger than 1 or less than 1? KEQ is bigger than 1. In diagram B, the position of the equilibrium sits more towards the left. In other words, the reactants. So the language we use around that is that the system favors the reactants. And that means that KEQ will be less than 1. Yes? Right? Okay, so I've got A and I got B. This is the right. This is the left. Yeah. Yeah. No. Good to ask for clarification, though. All right. I wonder if you can predict what the effect of an inert gas is on the equilibrium position. Can you? Effect of an inert gas on the equilibrium system? No idea? No? Or there's just no effect? No effect. You're right. Adding an inert gas and unreactive gas. Who are the unreactive gases? Who are the ones that we know for sure are unreactive? The noble gases to an equilibrium does not affect the concentrations of the reactant molecules. It does not make things go faster. It does not make them go slower. Therefore, the rates of the forward and reverse reactions are not effective, and therefore, what? Therefore, get rid of there is. That's, I need to fix that. Therefore, adding an inert gas causes no change. So, you should be so lucky as to be asked to draw a rate diagram for that, because what would everything look like? What would a concentration diagram look like? Yes? Nothing. Now, are you guys happy with that, or do you want me to walk through this little picture diagram thing? Walk through the picture diagram? Okay, so here we have some N2, some H2, and some NH3. The equilibrium with those is N2 plus 3H2 in equilibrium with 2NH3. And we have a concentration of, so the concentration of the N2 molecule here is equal to 4. Yes, I got 1, 2, 3, 4 N2s. And the concentration of the H2 molecule is 1, 2, 3, 4, 5, 6, 7, 8. And the concentration of the NH3 molecule is 1, 2. Okay? Now, when we add some helium, what have we done to the total pressure? The total pressure increases. And that's why some people are tempted to say, oh, the pressure increases, therefore we shift to the side with fewer gas molecules. But no, we don't, because what is the concentration of N2? It's the blue molecule. It's equal to 4. Yes? Blue molecule. How many blue molecules do we have? We have 4. Concentration of H2, which is the white molecule, we can go through and count. We got 1, 2, 3, 4, 5, 6, 7, 8. How many did we have before? We had 8. Oh gosh. All right, and the concentration of NH3 is still 2. There's 1 here and 1 here. Okay, so 2. If we have not changed the concentrations, has the frequency of collisions changed? No. Concentration is the same. Therefore, the frequency of collisions is the same. You will never need to explain this. You should know that an inert gas has no effect on anything. Forward, reverse. A, B, rate, time, concentration, time. And at this point right here, we add helium. And at this point right here, we add helium. And we see nothing. Nothing happens. Super fun. Is good? Okay. Now this one, the effect of changing the amount of a solid or a liquid. What do you know about solids and liquids and concentrations? They do not have concentrations. Concentration is not meaningful. How could I possibly dilute a solid? It's a solid, okay? Like this. This is a solid. How can I dilute it and still have it remain a solid? I can't. The number of particles per centimeter cubed is still the same. Like I can't do anything to it, otherwise it wouldn't be a solid anymore. It would be dissolved and it would be aqueous, okay? Same thing with a liquid. Can I, here I've got some water in here. Can I change the concentration of the water? No. Maybe if I had a liquid that was mixable with the water, but that's quite unusual. We don't do that very often. You might do that in organic chemistry, but not in like regular grade 12 chemistry, okay? So for the purposes of chemistry 12, you can consider water to be undilutable. Even if you put in a lot of solute, it is insignificant compared to the amount of water. The amount of water stays basically the same. The concentration of water is approximately the same, okay? So therefore, changing the amount of solid or liquid will cause no shift. Because you are not changing its concentration, you are not changing the number of collisions. Now, let's take a look at a solubility equilibrium, for example. Okay? This will be Unit 3, which I think will actually come after Unit 4 this year. Okay. And the reason it's going to come after Unit 4 is Unit 4, Mr. Colger does a really good job of teaching it, and so you're going to learn it over spring break. Not the whole thing, just the first little bit. Okay? You're going to learn the first little bit of Unit 4 with Mr. Colger over spring break. I know, you're like, spring break? I thought spring break was for relaxing. Well, you tell that to the people who took away 15 minutes of every class time, right? Because where did you think flex came from? Flex came from regular class time. So we have smaller amount of class time than we did before. Oh, and what about all those days when we do extra things that we didn't used to do? Like all the days when we have, you know, the semester changeover, and when we have like, you know, you guys are pulled out for this and you're pulled out for that. We didn't used to have those. We just taught and we did more labs and we taught more things and we got through the course in the time allotted because that was what we did. But now we don't have as much time. So you get homework over spring break. Otherwise, you go off to university not knowing some of the units. Okay. Here is an ionic crystal lattice. We have a metal. The metal is positive. We have a nonmetal, which is negative. Yes. And here we have a crystal. Okay, we toss it into the water, and let's say that whole dang thing dissolves. Okay? When it dissolves, the ions do what? They dissociate. Okay, so that's what that looks like. Now, eventually, if we add more solid, what will happen to our solution eventually? We add more solid, we stir it, it disappears. We add more solid, we stir it, it disappears. Eventually, if we add enough solid, what will happen? It won't disappear anymore because the solution will be full. Yes? it will contain as much solute as possible. Does anyone know the word for a solution that contains as much solute as possible? A solution containing as much solute as possible is called a something or other solution. Saturated. Thank you. Nice work. Have you heard the word saturated before? Yeah. Yeah? Okay, that's what it means. It contains the most possible. Any of you taking biology? Have you heard of saturated fats? That means it contains as many hydrogens as possible. There's no double bonds. Ah, yes. So it's a similar kind of concept. So we're going to add more solid and we're going to stir and we're going to add more solid and we're going to stir. And eventually we will end up with a solution where no more solute dissolves and the solution becomes saturated. So there is a limit to the concentration of the ions in solution, and that's what Unit 3 is going to be all about, is these saturated solutions. Now, once a solution is saturated, it means that in solution we're going to have 1 M plus for every 1 mx that dissolves. For every 1 mx that dissolves. So what that means is we get an M coming off and an X coming off. Because it is saturated, we have to be at equilibrium, right? Because we can't dissolve anymore. Okay, if this is saturated, can I fit any more ions in there? No. So if 2 more ions dissolve, what has to happen to another pair of ions? They have to precipitate. Are you guys familiar with the word precipitate? Okay. Also known as recrystallize. Over here, we have dissolving, and over on the right, we have recrystallizing. Now, take a look at the surface of that crystal, right? Take a look at the surface of this crystal. Would I be able to have more than 1 mx dissolving at a time and 1 mx precipitating? Is there anywhere else for the mx to come off? We've got this M coming off. We've got this X coming off. Is there anywhere else that is available for mx to dissolve? Kind of, maybe down here. Yes. Maybe over here, but that's where things are busy precipitating, right? So when you have a small crystal, there are few sites for dissolving and recrystallizing. Has a small area available for dissolving and recrystallizing. So I might be able to get more than one particle to go into solution and out of solution, but not much more. Okay. What if I add more solid though? Am I going to be able to dissolve more ions? If we add more solid, can we dissolve more ions? Remember, this solution is saturated. What does saturated mean? It contains as much solute as possible. So if I add more solid to this already saturated solution, can I dissolve more ions? No, because I already have as much solute as possible dissolved. Does that mean that the dissolving process stops? Yeah, we still have the dissolving process happening. Yes. M dissolves, X dissolves. But for every M and X that dissolve, I can have another M and another X that recrystallize. And remember, before we could only have like one particle dissolving and one particle precipitating because the surface was very small. Now we have a larger surface. Yes? So could I have this M coming off here and this X coming off here? Sure. But what would have to happen? I would have to have another one precipitate. Okay. And if I have another one coming off, M coming off, X coming off, uh-oh, this is going to get messy. However, I could have another M come over here and an X come over here because I have all of that surface available, yes? So what has happened to the rate of dissolving compared with diagram A? Here's diagram A, here's diagram B. What can you say about the rate of dissolving in diagram B? Rate of dissolving is, remember the red arrows are the rate of dissolving. How many red arrows in diagram A? 2. So the rate is 2. How many red arrows in diagram B? 6. So the rate is 6. Yes? So in diagram B, the rate of dissolving is higher. What about the rate of precipitating? It's also higher. We have 2 green arrows in diagram A. We have 6 green arrows in diagram B. So the rate of recrystallizing is also faster because you provided a bigger surface at which that process can occur. Okay? Now, am I going to ask you about this in Unit 1? Not so much. I'm not going to ask you to describe this, but you should know that adding a solid does not change the position of the equilibrium. You cannot make more solid dissolve when it's already saturated by adding more solid. Yes? So what that means is that if I have a reaction like this, mx solid in equilibrium with m plus x minus, and if I'm at equilibrium, that means I am already saturated, okay? If I increase the amount of mx, will there be a shift? No shift. Okay, because it is a solid, you cannot change its concentration. If I were to increase the concentration of M, I could make it shift towards the reactants because M has a concentration. It is an ion. If I increase the concentration of X, I could make it shift, but I cannot make a reaction shift by adding a solid or a liquid. Is good? Okay. (2.2f). This is just a very brief making quick predictions. If you have a concentration and you increase it, the system shifts away from the increase. If you have a concentration and it decreases, it shifts towards the decrease. Temperature, if we increase the temperature, it shifts away from the heat term. If we have temperature and it decreases, it shifts towards the heat term. You should be able to explain all of these and why they happen, but this is just like a quick reference page if you're like, I just want to know fast. Volume. If I increase the volume, will I shift to the side with more molecules or will I shift to the side with less molecules? I've made the space bigger. What do I need? Do I need fewer molecules to fill that big space, or do I need more molecules to fill that big space? I need more molecules. So we're going to shift towards the side with a larger total amount of gaseous entities. Wow, that's a really weird way of phrasing it. I need to redo this table. I stole it from somewhere, obviously. Toward the side with a larger amount of gas. There we go. Molecules. Gaseous entities. Gas molecules. There we go. Okay, and if we decrease it, squish. We have less space. Will we shift to the side with more molecules or fewer molecules? Fewer molecules, because we got less space, we want fewer molecules. Okay? So if we decrease the volume, we shift towards the side with the smaller amount of gas molecules. Do you remember last week I said you need to talk about gas molecules when we talk about shifting due to pressure? You can't just say molecules, you need to say gas molecules. Okay? Catalysts have no effect, inert gases have no effect. We have some practice here. So if we look at this, quick fire practice. Ooh, exciting. It makes it sound like so much fun, right? No, okay, that's all right. That's all right. We're going to pretend it's super fun. Given the following reaction, describe the changes that occur after the stress is applied. So we're talking about the shift. Okay, so after the stress is applied, what happens during the shift? So if we increase the concentration of N2, we shift to the, and you might not want to draw this because you're going to need this reaction many times. It's going to shift to the right. And what's going to happen to the concentration of N2? We're going to decrease because we're using it up. Concentration of H2 is going to decrease because we're using it up. And concentration of NH3 is going to increase because we are producing it. All right? If we decrease the concentration of H2, then we're going to shift to the left. We're going to be making N2 and H2, so those two are going to go up, and NH3 is going to be used up, so it's going to go down. All right, you're going to try these ones as quick as you can. You're going to do the same thing here, and the only thing is you're going to describe, so on page 2, you're going to describe the change in concentration due to the shift. And so N2O4, because it's got a coefficient of 1, let's just say N2O4 is increased, it will shift to the right. N2O4 is going to go down then by 1x, and NO2 is going to go up by 2x. I don't know if you actually need to do the 1x and 2x here, but I know you do on the next page, so, you know, or somewhere like that. So there we go. Okay, so just give all of those a try. See how fast you can get. So you're working on pages 62 to 66. When you get to the end of any one page, I would check the answers and see how you're doing, okay? Oh, just ignore the X's for now, okay? Ignore the X's, I don't think they're in there. Yeah. But when you did, they were from the coefficients. Oh, yeah. And if anyone's interested in seeing how well our, do you remember we made Papa 1 and it was green? Guess what color it is now? It's blue, but I've been feeding it aluminum foil, and it's been eating the aluminum foil. I'm going to have aluminum ions now, and it's turning into copper solid. The reason we're doing this is that copper-2 ions are really toxic for the environment. We don't want to throw them down the drain. So what we're going to do is convert all the copper into copper-0, which is the solid copper, and then filter it out and collect it. And then it's not toxic. And then we'll have aluminum ions to throw down the drain, which are also not toxic. I'm going to feed it some more aluminum foil.
But since it has more, it's gonna decrease now.
You got it? It is long. That's what about a long time. Hello. No, it's not equal. So if it's not equal, then it's a half of the essence.
So yeah, you're real. I know.
Okay. Yeah. So pressure is small. And there's not enough carbon dancing.
Yes, that's what I do.
More molecules of gas. You have to take down one negative so that there will be more thing sides of the organization. On this side, it's really tough one. Expand the space. It's going to be more down.
I know. It's fine.
Okay, so
You didn't bring back down. It's like Inert.
Anybody questions?
Oh, yeah, yeah, it's like, yeah, I can see. No, I don't.
Girls, they're all gals. 2, 3, it's actually right. Because it's what's the place? I was dating. I was like, wait, why did I
So it's left. Well, you may shift towards the side. Yeah. Yeah, because we increase the pressure, right? That's right.
Oh, we're decreasing the pressure. Yeah, my bad. So it's like, that's the thing that's the back. Okay, so like, we're supposed to go left because it's like
More down, more down. It's like that. Yeah. Anyone got questions here? Good stuff. Yes.
So, decrease really, right?
So if the temperature is decreased, the reverse rate will decrease more.
So,
So quite frankly, the easiest way to think about it is you can treat this as though it's a product, okay? You're decreasing the amount of heat. So the system is going to shift to release more heat, which will make the temperature increase. Okay? Yeah. Okay, yeah. Yeah, okay. So what we're going to do is for temperature, this term here, you're going to treat it when the increased temperature, we increase the amount of heat. When we decrease temperature, we decrease the we're decreasing. Now, it'll shift to the right, right? Now, why is it doing that? It's because if you decrease temperature, the particles are going to move slower. So we want to release some energy to make the particles faster. Yeah. And then volume is all about trying to get the pressure
back to where it was. So if we increase, sorry, if we increase the volume, now there's more liquids with the side. We would like to fit so that there's fewer gas particles, so there's fewer collisions with the sides of the mirror like there were before when it was a bigger size. Okay, now in this case, we have two gas molecules here. We also have two gas molecules here. So can we fix this problem by shifting? So it's just gonna stay the same. Yeah, so if you increase the volume, you have more particles to bring it back.
So the white look here.
Yeah, because there's 1, 2, 3, 4. Over here, there's 1, 2. So increase the volume. You want to take 2 particles and turn them into 4 particles. That way we'll have that. Yes. Or, yeah. And if we increase the pressure, that way it's more. Yeah.